Swayam Prabha. Digital India. Educated India.
The 5.7 critical difference we have achieved based on 4 plugs as per the norms, but there may be some situation where we have not tested the specimen based on the 4 plugs. We have tested say 2 plugs, so we have small quantity of specimen, and for that we have tested, we have got the 2 such plugs for micronear, and in that case should we use the reference as 6 critical difference or not, that let us see. So if the recommended number of tests are not performed, so number of tests was 4, but we have performed only the 2 number of tests, so how the critical difference is getting changed? So new critical difference will be based on this. This is the new critical difference. So earlier, as per the table, critical difference it is 6. Now our number of though actually 4 was the required, okay, and this the N2 is the our recommended number of sample. So 2, and what we have done, 2 was the thing and 4, so our critical difference requirement will be changed, okay, in recommended number and into number of tests actually conducted. So N1 is here is 4 recommended, N2 is 2. So that way we can, and it's under root this 2, that means 6 multiplied by 4 by 2 under root, so 6 under root 2. So in this way we will come to know the number of specimen, number of what is the new critical difference, okay. So the accuracy of test data, as we know, if we test the more number of sample specimen, then the accuracy will be better. So this part we have already discussed, that I have explained this zoning technique. Now let us see the animation. Through the animation we can see, so as I have explained, these are the small specimens we have divided into different zones, and then this each zone is divided into 2 parts. One red parts are discarded, and then remaining half portions of each zone is kept. Then again we are dividing into further 2 parts, and 1 part is discarded. In this way this process will continue till the required quantity of material is actually obtained. So this way it will continue, and we will get finally our required number of sample. So here say let's say 40 zones we are taking. Each tub that takes specific proportion from each tub, and what you have to do, you have to actually see also it's free from any damage. We have to take the specimen which is free from any damage. Okay, so divide the samples into 4 quarters. So you can have this is different types of zoning technique is explained here. So I'll show you. This is the another zoning technique. Here you can see that here 4 zones you are taking, and then from here 16 small tubs you are creating. Okay, then 1 tuft you are taking here, and then you are again dividing it to 4 subgroups, some small tubs. Then you take randomly 1 tuft. So first tuft from the group 1, second, third, fourth. This way you can create a smaller sample. Okay, so we can actually define our own zoning technique. Here, as I have already explained, so the lengthwise we are dividing into 2 parts. Then again widthwise we are dividing into 2 parts, and 1 part is rejected. Then again lengthwise, widthwise. Ultimately we are getting very small tuft. Okay, so these are explained here. First, each small tuft shall be halved several times. Discard alternately with right and left hand, as I have explained. Turning the tuft through a right angle. So you are turning it because one is lengthwise, and then we are turning it. In this way we will go. So each time we are turning it to its right angle, so that we are again randomizing the position. Okay, so 16 such whips will be taken. Okay, 4 set of 16 whips are taken. Combine each 4 set and mix the tuft, double and draw, so that we are doubling and drawing and doubling, so that we are getting the random specimen. So then again dividing it to 4 parts. As I have explained, 1 tuft, part 1 of tuft 1, part 1 of tuft 2, part 1 of tuft 3, part 1 of tuft 4. In this way, then part 2 of tuft 1. In this way, we will get the 4 new tufts. So this is the explained here. So what we are doing, this is tuft, different tufts. We divide into 4 sub tufts, small tufts. Then part 1 of this tuft we are taking all part 1. So we are getting 1 tuft. Then part 2 again we are getting final. So in each time what we are doing, we are actually eliminating or rejecting the half portion of this. Okay, so this is another technique of zoning technique. Next comes the core sampling technique, and core sampling technique, as I have mentioned, this technique is mainly for wool fiber, where In cotton fiber, we use zoning technique because cotton fiber tuft can be taken easily by hand without any much effort. But for wool fiber, as wool fiber, you will see it's a compact solid. And it's very difficult to take out the fiber. Even a single fiber, taking out single fiber is very difficult. And in that case, separating the fibers will be very difficult. For that, what we do, we use core sampling technique. Coring tubes are there which will cut the fiber. So when the fiber, a tube is there, coring tubes, narrow coring tubes, and which is hollow tube at the. So this is, suppose this is a tube where at the tip, this is the tip of the tube. This is at this portion, it's a very sharp. It's a knife sharp, and this core inside is hollow. When we push this coring tube inside the bell, that means fibers are cut and it's penetrating. And what we get inside the coring tube, cut fibers are there. Small cut fibers are inside, okay? And as the fibers are being cut, that means we cannot test the fiber length. Fibers are already cut. What we do, we can test the grease content, vegetable matter inside that thing, diameter of the fiber. So these things we can test, but not the fiber length. And also moisture content in the inside the bell, but not for the fiber length as it is being cut. Now you can see this is the coring tube, where here this is the cutting tip which is very sharp, and when it penetrates inside the bell, the fibers are cut, it penetrates inside, and the length of the coring tube is such that the coring tube at least penetrates at the center of the bell, that is half of the length of the bell. So when we penetrate the bell, and so that it collects the fiber from the center, and there is a tapper at the edge which ensure that fibers are cutting and the small cut fibers are penetrating into the hollow tube. And when we tilt it top side in this way, this is the coring tube, and when we tilt it at the 90 degree, then the fibers present inside the coring tube, it fall into, this is the plastic core bag. Why is it plastic? Because here it should be airtight. Whatever moisture present inside the fiber, if we want to test the moisture content, the moisture present in the bell is and the fibers with that level of moisture is inside, and after several time its coring penetration and repeated tilting it, the fibers are sufficient fibers are collected, and then this plastic bag is taken out, and this is covered with it's tied down so that it is free from other moisture. It cannot take or release the extra moisture. Okay, now try to see the animation here. Core sampling. The raw wool box is the bag is there, but bale is there, and it's hydraulic coring machine. It's not manual. It's hydraulically pressed inside the end, and then the fibers are cut fibers are penetrated and it's tilted 90 degree, so that the fibers are actually, the whatever fibers are there, it is inside, it comes inside the plastic bag, and then again from the other side, and we continue these things from different side of the. So that means it ensures that we are taking fibers randomly from different location of the bale, but without disturbing without opening the bale, without disturbing the bale. Small quantity of fibers are being taken. So after this, so you can see that coring tube length is approximately 2 feet, which is typically half of the bale size. Okay, so that it ensures you are penetrating at the center of the bale. So the basic thing is that our understanding is that we want to know, suppose someone is actually putting the fibers, the bale fibers, while at the outside he is giving a good quality fiber with a lower moisture content, grease content, but he is trying to mix the fiber with a higher grease content, higher moisture content at the core center. So that type of malpractices can be actually avoided by coring. Otherwise, if without core sampling, you can maximum take the sample from the side. That will give you wrong result. So tube enters in the direction of compression. Okay. So basically what happened, in the direction of compression means the fibers are compressed in this direction. So while making the bale, fibers are compressed. So that in that direction the coring tube will be there. Coring tube will penetrate. In other direction, if it is there, then fibers are sometimes it's in a vertical condition. So that way it will not. Suppose when we are making the bale, suppose this we are trying to make the bale. So these are the fibers. Okay, these are the fibers, and the fibers are compressed in this fashion, and coring tube will be penetrating from the top. So that is the direction we need, perpendicular to the layers of fleece, so that fibers are cut. Cutting tube diameter is less than the core diameter, because it helps in the proper penetration of fibers into the hollow tube. Sliding of the fibers in the coring tube. Cleaning the core as it would. So why is it another function is that inside the bale the fibers are at a very compressed stage. When cutting, the fibers will actually will expand. To enhance, to actually facilitate proper sliding of fibers, you need this type of conical shape. And number said that, as I have said, number of cores are extracted and combined. So the different size of tubes are there. Container, it's kept into the container immediately. Hydraulic coring machine is used. Okay. And next is that fiber sampling from sliver or yarn or roving. This is the sliver. And fiber sampling from sliver, yarn, roving, as I have mentioned earlier, this is called numerical sampling, where when we take the fibers from the tip, this is not affecting the, it is not actually governed by the fiber length. So here, very difficult to obtain unbiased sample, because unless the special precautions are taken, the longer fibers are being selected. So this is the, from here, it's very difficult to take the unbiased sample. So, but from sliver, roving or yarn, the fibers are randomly arranged longitudinally. This is the process which we have done already in carding draw frame. Okay. Unbiased sampling. So this is the sampling roving fibers from roving sliver and yarn. And unbiased sampling we can make using the numerical sampling. Another way of sampling is you prepare the bias sampling, then length bias sampling in such a way that the bias can be allowed to do any calculation based on some assumptions. So that's an important thing. Where length bias cannot be avoided, then we will do away by some assumptions. Let us try to see here. Here we are talking about the numerical sampling. Now these are the different fibers. Now when we take the fibers from so this picture represents the numerical sampling like a sliver. Inside the sliver, these are the different fibers. Now when I am taking the fibers by gripping point A, the line A, so and I am pulling it. So the fibers which are crossing the line A are gripped and being pulled, which is shown by blue colors. But remaining fibers, which are red and green fibers, are unaffected, irrespective of length. Now next, after A, then I am again gripping B. So C is getting unaffected. Then I am gripping C. Then D is getting unaffected. In this way, I will keep on taking the sample, and then I will put together everything. These samples are length unbiased sample, that is numerical sample. Here we will find all the sample proportion of all the fibers are unaffected. Okay, there is no length biasness. So this is explained here. Okay, and what about length bias sample? Now in length bias sample, as we have discussed, you cannot avoid this type of sampling where we take the fibers from the surface. There the proportion of fibers in the group of sample, suppose this is here it's a fiber and the fibers are there say fibers of 30 millimeter, 40 millimeter and 50 millimeter. So these fibers are mixed as a 1:1:1. Equal proportion of fibers are there. So Ly is the fiber of length with fiber with Y% in gram in bulk. So that means 30 millimeter is the Ly and 1%, 1 proportion. So 1, 41 and 51. Okay. Y% is there. Now let us take one example. So we have got say 10 millimeter fiber, 15% of 10 millimeter fiber in the bulk. Okay. So 15% fibers are of say 10 millimeter fiber, 15%, 20 millimeter fiber, 15% fibers are there, and 30 millimeter fiber, 15%. So there will be other fibers are there. We are only talking about the three different fiber length: 10 millimeter, 20 millimeter, 30 millimeter, and their proportion is 15%, 15%, 15%. Maybe 40 millimeter, maybe 20%, and 50 millimeter, maybe 45%, like that. Total will be 100%. So we are considering only three different fibers. So 10, 20, 30, and their proportion is 1:1:1 because it's a equal proportion here. And then X1 will become X1. What is X1? These fibers, 10 millimeters fibers, proportion in bulk. So here the proportion of 10 millimeter in the bulk will be, you just multiply, it will become 150. Here 20 millimeter into 15, 300. So 30 millimeter in 15, 450. Okay. So if we take the proportion here, 1:2:3. The proportion, so X1 is the proportion. So ultimately, finally, its proportion will be 1:2:3. What does it mean? Although in the bulk, 10 millimeter, 20 millimeter, 30 millimeter fibers proportion are equal, but when we take the sample from the surface, due to the longer fibers presence, that means longer fibers are selected preferentially. So its proportion has become 3. Okay, 20 millimeters proportion has become 2. So this is the concept here. That means longer fiber will have higher chance of being selected. This we will discuss in detail when we will discuss the fibrograph, where fibrosampler is there. That we will discuss in detail there, and what are their implications. So the random tuft is here, and this AB is basically, you can see that A, B different zone. If we pick the A or B, whatever fibers are crossing that point, that fiber will be selected. Like here, I am picking this point, like A. A is a line. Whatever fibers are crossing in this line will be picked, and here the selection point is that the longer fibers are selecting preferentially. That's why it's called the length bias sample. And when we select the length bias sample, that means this is the bulk, and we may consider this bulk as a normal distribution, blue color. There is a bulk sample. The fiber lengthwise distribution is long. This length bias sample, that's a normal distribution. But when we are taking the length bias sample, that means fiber length will be shifted rightward. So this is the normal sampling. You can say it's a numerical sampling, blue color, and the length bias sampling, it's a represented by the red color. So how to prepare this sample we will discuss subsequently. Now here, this is a clamp, as I have mentioned. This clamp, where we select the clamp here, the crossing point is this. This is the clamping point. But ultimately the fibers are, if we in the fringe, fibers are in the loop form. It forms the loop because we are gripping the fibers randomly at certain point. So this is the fiber we are gripping at certain point. So this is the point, and the fibers this fiber will be folded. This is the gripping point. So this way, this fiber is folded here. This fiber is folded in this fashion. They are forming up loops. This fiber is peaked at almost at the tip. So you can see this side end, the right side end has become made a smaller side, and this fold, this is this person. Ultimately, it is making the loop, and we will measure all the fiber length in the length measurement. That we will discuss subsequently. So here, while picking the fiber, while taking the fiber specimen, the two assumptions are there. One assumption is that a fiber is caught on the comb, this is a clamp or comb, in a proportion to its length as compared to the total length of fiber in the sample. That means a longer fiber will have higher proportion of being selected, greater chance. And second one is that the point where it is cut is at random along its length. It's not that always the fibers at the center will be picked, because this is fibers are randomly selected, and it will be picked at random fashion. So this is cotton with a different. Now here in this picture, the fibers, to show the point, second point, to prove the second point, what we have taken here, the fibers are of equal length. You can see approximately fibers are of equal length here. Now when we pick the fibers randomly at so this fiber, say this fiber, this one is picked at the center, this fiber is picked at the end point, and all other fibers are picked at different points along the length. So it shows the fibers are picked at randomly at any point, and ultimately this is forming loop. This forms a loop. Now, this clamp is used in the fibrogram for scanning. That we will discuss when we will discuss the fibrogram. This is this will create a fibrogram. Now let us see one numerical based on the random length bias sampling. The ratio of the proportion of individual fiber in a blended bulk fiber containing 40 millimeter, 30 millimeter and 20 millimeter fibers. Three different fibers are blended with the proportion of 1:2:3 respectively. These fibers are blended. Now what we are doing, we are taking the random sampling. We are taking the length bias sampling by this type, that fibrogram type of grip. The proportion of length group of 40 millimeter, 30 millimeter and 20 millimeter fibers in the length bias sampling drawn from the sample. So one is length bias sampling, another is the numerical sampling. If we have this type of this proportion of fiber in a sliver, and if we take the numerical sampling, the probability is that in the numerical sampling the proportion will remain same, 1:2:3. Okay, but when we take the length bias sampling, the proportion would be, so x1, which is proportional in the bulk in the sample, is proportional to the length and y in the bulk, proportion in the bulk. So x is the proportional of the length group in the sample, Ly is the length of the fiber proportion in the bulk, and y is the, so you can see 1:2:3. So 40 multiplied by 1, this y is the proportion in the bulk. Okay, so 30 multiplied by 2 and 20 multiplied by 3. So if we, and we are getting the proportion, so you can see here, though ultimately it becomes 2:3:3. So this is the proportion which is changed based on the, due to the presence of fiber length. Okay, so this, with this we can get the proportion in the sample. So another example which is similar example, just 60:40:20 and 1:2:3, and what will be the proportion in the bulk? The same, in the same way we will get the proportion 3:4:3. So we see that based on the whatever way you mix in the bulk, if the fiber length is changed, then the proportion in the specimen will get changed. So if we know these assumptions are broadly, it's valid assumptions. Okay, and if we know these assumptions, and based on these assumptions we can predict the proportion of these fibers in the sample. And for fibrogram, in opto-electric method, the fiber length where the density of fibers are taken into consideration. Sample is prepared by fibro sampler. So fiber length measurement. So this is the principle of fibro sampler is that we take the fiber and press against an opening, then through the clamp we clamp the fibers in this fashion. This is the clamp, and here it's a clamp, and this picture is like earlier we have shown the same fiber length we are taking, and the loop is being formed, and these fibers, and here it's a scanning is taking place. In optical scanning is taking place here, where the number of fibers are counted. This we will discuss in the fiber length measurement module. Now, fiber sampling from sliver. So the system we have discussed, this is the sliver, and we remove some fibers from the edge till the longest fibers are removed, so that because there is always possibility that edge fibers may be damaged. So after the longest fibers are removed, then all the natural length fibers are taken out one by one, and we collect it in a velvet pad, and those fibers are tested for some parameters. Now let us see the animation here. This is a random draw method. You can see initially some fibers are removed to get the natural length. Now after that we are taking out, this is called first draw, then second draw. In this way we will keep on taking the fibers, collecting the fibers, and these fiber samples are tested. And this is actually, these fibers are basically it's a numerical sample, okay, where length biasness is not there. And in case of sliver, it's easy to take out fibers because the fibers are almost parallel, so there is no restriction. So this is actually a numerical sample. Getting numerical sample is easy, okay. So the fiber specimen will be free from bias, and which is typically numerical sampling. Now the problem comes when there is a twist like a roving or yarn. When there is twist, it's very difficult to take the fibers from the in numerical sampling method. In that case, in case of roving and yarn, first thing we have to do, we have to untwist the strand to make the fiber strand parallel, and then after untwisting, when the fibers are parallel, then it's easy to take out the fibers. We can easily take out the fibers, and that's how it's a roving and yarn, which is known as the cut square method. cut square method means first you cut the yarn or roving and then untwist it and then follow the similar techniques. Let us see the cut square technique. So yarn or roving is there. First you rotate the tip to make it untwisted. It is untwisting it, untwisting the twisted yarn, then after that it is becoming parallel. Then we will be discarding some small portion from the tip similar to earlier process. Just discard out and then we'll collect the fibers and we are discarding this. When the fibers are become natural length, and then we collect the fiber using the grip and then keeping the sample on the board for testing various parameters, maybe fiber strength, length, whatever. So this is the method, cut square. So you can see that we are collecting the different specimens. So cut square method, where cut and then projected fibers are discarded. First you are cutting, then projected fibers are discarded little initially. Few millimeter, then natural lengths are without cut are taken. Okay. And yarn sampling is that here for till now what we have discussed, how to take the fiber sampling. Now yarn sampling is very simple. You use the random table depending on the requirement and number of samples in the bulk, number of bobbins in the bulk. So we use our random sampling technique. If total 10 packages are to be selected from a consignment, from random consignment contains more than 5 bags. If it is more than 5 bags, they are selected at random from it. Then 2 packages are selected at random. That means 10 cones you have to select. So 5 bags, more than 5 bags are there. So first select 5 bags. Then from there you select 2 cones per bags. If the bags are less, then use all the bags, and suppose 3 bags are there, randomly you select from that. Typically almost equal in that from each bales. Count of yarn removed from the fabric. Now we have to test the yarn count to be removed, which is removed from the fabric. Now the issue is here for fabric. Suppose we want to use measure the yarn count or strength, yarn strength from fabric, or even fabric strength or whatever maybe. This is the fabric. Here it's warp. Okay, wave direction. Now can we take fabric specimen from this side. We should not take, because we should avoid the selvage. Now, if we want to take this is one specimen and another specimen is this, and we want to test the yarn strength of warp yarn strength. So this is one specimen and this cannot be taken, because here same set of warp is taken. So instead, if it is a warp testing is there, either we can test this side or we should take a sample from. This is correct approach, because here again wefts are common, so we should not use the same warp or weft. But if we test the yarn strength, then this two is okay. This is okay, and this is also okay. Okay, because same different set of yarns has to be taken. Cut 2 warp and 5 weft. Okay, so rectangular strips, 2 for warp, 5 for weft. So why 5 for weft? Why 2 for warp only? Because 5 weft we normally take from different. We normally take weft from different packages. So there may be some variability. So that you must use different higher number of weft is there. So warp is actually taken from a longer length. So 2 warps are there. So normal size is that 20-inch length. So we have to use the 20-inch length here, cut, and width at least 50 threads. So this width you have to take at least where 50 threads are there. Different warp or weft in each rectangles. So different rectangles you have to take. And if you want to test the yarn twist, so specimen in equal number from 10 packages you have to take. No specimen within 1 yard at the end of the pack, because the twist may get it may get untwisted at the edge. Okay, end point. Minimum 1 yard distance between 2 consecutive specimens should be there. And least strength of span yarn, so 20 complete leads you have to take, each from 20 packages. If the number of packages are less than 20, then 20 leads are selected equal from each package. So 20 leads you have to take it. Okay. And fabric sampling, as we have already mentioned, so we cannot take these two together. So we should take this sample and this sample, this specimen. This, if we take this one, this is first sample. Second sample, if we take this one, so that means warp common. If we take third sample, this one, this is weft common. So we should sample 2 will be this one. Okay. So in this way we can take fabric sample. Warp direction should be marked before we cut. These are the steps. No 2 warp specimens should contain the same warp or weft. So no 2 fabric specimen should take same warp and weft. That we have to take that care. Because if we want to suppose if we want to test strength specimen 1, specimen 2, if these two specimens we take, the problem would be there, although we are testing warp strength, but same warp wefts are there. So basically for strength testing, the warp-wise strength testing, weft also take part. So that to eliminate this variability, so we must take the specimen in such a fashion, no two specimen contain same warp and weft, okay? And sample should not be from within 50 millimeter of selvage. So selvage we should actually avoid at least 50 millimeter distance from, because selvage is sometimes selvage gets damaged. So till now what we have discussed, the sampling technique of fibers, yarns and fabrics, and what we have got till now, we have got sufficient material with us for testing. So we have got fiber sample, unbiased fiber sample, or even lead biased fiber sample, yarn sample, fabric sample, where we have applied different techniques to collect the sample, and like our statistical sampling, non-statistical sampling, for fiber, zoning technique, core sampling technique, fabric. So now we can imagine with us different types of samples are there, which is actually as per the standard procedure. Now what we have to do, we have to, these specimen samples are ready for testing, and testing we will be doing subsequently. Before that, let us consider that we have tested all the samples which we have collected, and this samples testing. Now how to do the analysis, like the significance test or confidence interval. So basic statistics we will be using, practical statistics. I'm again repeating, we will not be doing any statistical class, but the how to handle the test data, for that we will discuss some practical statistics, and that we will discuss in the next class. Till then, thank you.